Good morning, folks. This is Mike. How are you all doing? I'm doing well, I know that much. Coming at you with another video on college algebra. In this video, we are going to continue our discussion of matrices. We're going to talk about a special kind of matrix. Then we're going to talk about the multiplicative inverse of certain kinds of matrices. So getting right into it, we put a lot of focus on matrices that have the same number of rows as columns. A matrix with the same number of rows as columns is referred to as a square matrix. And before we get into the video and the main points of what I want to go over, I just need to introduce a particular phrase. The main diagonal of a square matrix consists of all entries going in a straight line from the upper left corner of the matrix to the lower right corner. So I've sketched the main diagonal. I've dashed it in red for a 2x2 and a 3x3 matrix here. A, B, C, D, the main diagonal is A and D. In the 3x3 matrix, our main diagonal is A, E, I. Those are the entries or the elements of the main diagonal. So upper left-hand corner down to lower right-hand corner going in a straight line. For matrix multiplication, if we have a square matrix, we do have a matrix so that if you take your given matrix A and multiply it by this special matrix, you're always going to get out the matrix A that you had to start with. It's called the identity matrix, the n by n identity matrix, and we denote it by I sub n. It's the matrix with all entries on the main diagonal being ones, and all other entries in the matrix or all other elements of the matrix are zeros. These are the identity matrices for a 2x2 matrix and a 3x3 matrix. You can see all entries are zeros except for the ones on the main diagonal, and those are all ones. And there is a special property that this identity matrix has. For any n by n matrix A times I sub n equals A, and I sub n times A is equal to A. And what we're saying here is that if you multiply by the identity matrix, then matrix multiplication is going to be commutative. The order in which we multiply those matrices does not matter. And this is very special for this matrix because in general, commutativity of matrix multiplication is not generally true. It's not always the case that if you have the product matrix AB and the product matrix BA, it's generally not true that those two things are going to be the same thing. In fact, in many cases, if you're trying to multiply two matrices, not necessarily square matrices, but just any two matrices, many times you can't even find both of those product matrices, A, B, and BA. Many times you can only find one. So when you're multiplying by the identity matrix, the matrix multiplication is commutative. But now we're going to see another type of matrix where if you multiply it, it is commutative as well. So let A be an n by n square matrix, and let I sub n be the n by n identity matrix. If there is an n by n matrix, A with the little exponent of -1, we read that as A inverse, such that A times A inverse equals I sub n, and A inverse times A equals I sub n. Then, as you can probably guess, A inverse is the multiplicative inverse of A. Certain n by n matrices, if they have a particular property, which we'll get to that property a little bit later on in this chapter, if your matrix has that particular property, then there is this multiplicative inverse for that matrix. And we verify that it's the inverse by doing both of these calculations here. A times A inverse, and then A inverse times A. And if both of those give us the identity matrix, then we're good. So here, just a sample problem for verification. Let's verify that the inverse of A here is going to be this guy right here. Let's verify that the inverse of 5, 3, 3, 2 is 2, negative 3, negative 3, and 5. So I'm going to do A times A inverse. 5, 3, 3, 2 times 2, negative 3, negative 3, 5. And now we're just going to do our basic matrix multiplication like we learned from our previous videos. I'm taking the product of a 2 by 2 and a 2 by 2. So I know that my product matrix here is going to be a 2 by 2 matrix. Entry in first row, first column, first row, first column. Product of the firsts plus product of the seconds. 5 times 2 is 10. 3 times negative 3 is negative 9. 10 plus a negative 9 is a 1. Entry in first row, second column. First row, second column. Product of the firsts, negative 15. Product of the seconds, positive 15. Add those up, we get 0. All right. Entry in second row, first column. Second row, first column. Product of the firsts is 6. Product of the seconds is negative 6. Add those up, we get 0. And second row, second column, second row, second column. Product of the firsts, negative 9. Product of the seconds, 10. Negative 9 plus 10 is a 1. And obviously this is the 2 by 2 identity matrix. We have to verify it the other way. Do A inverse times A now. So 2, negative 3, negative 3, 5, and 5, 3, 3, 2. And now I'm going to let you do the matrix multiplication here on your own. Pause the video here and see if you come up with the 2 by 2 identity matrix. So as I said, pause it now. Once you think you have your matrix multiplication done, press play and we'll see if you had the correct multiplication. All right, so let's see if you indeed came up with the 2 by 2 identity matrix. Entry in first row, first column, 10 minus 9 is 1. Second row, first column, negative 15, positive 15 gives me 0. First row, second column, 6 minus 6 gives me 0. And then second row, second column, negative 9 plus 10 is a positive 1. So we do indeed get the 2 by 2 identity matrix. And yes, we have verified that the inverse of the matrix A is this matrix right here, 2, negative 3, and positive 5. So what sort of method do we have that we can use to figure out the inverse of any n by n matrix A, and that is if the matrix has an inverse. We are going to learn in our next video when a matrix has an inverse or not. So here's a general method that we can use to find the inverse of any size matrix, really. But again, we're going to focus on 2x2s and 3x3s. So first thing you're going to do is you're going to take your n by n matrix, and to the right of it, you're going to add on the n by n identity matrix. And you're going to get this significantly larger matrix. So you're going to write this matrix A, the matrix you were given, and then to the right of it, you tack on the n by n identity matrix. You're going to use those row operations that we talked about all the way back at the beginning of this chapter to write the matrix and turn that matrix into the form the n by n identity matrix, and then you're going to have some matrix after that. That matrix that you have after the n by n identity matrix, that is going to be the inverse of the matrix that you were given. So we're going to do a sample of each, one 2x2 and one 3x3, but we are going to employ the use of our calculator to help us get there just a little bit quicker. So we're going to find the inverse of this matrix here, 5, 38, 1, and 8. So I'm going to write this matrix, and then also to the right of it, I'm going to tack on the 2x2 identity matrix. And you can even draw that dashed line there if you want, just as sort of a mental note so we know that, oh, this is what we're doing. And now we would try to put this matrix in row-reduced echelon form. That's actually what we're doing here when we say in step 2 we want to write it like this. We're actually just taking our matrix and putting it in row-reduced echelon form, just like we did in several of our previous videos. So I'm going to create a new matrix here. It's a 2x4 matrix. So 5, 38, 1, 0, and 1, 8, 0, 1. And I'm going to, as I said, I'm going to take this matrix and put it in row-reduced echelon form. And when I do that, with a magical touch from our calculator, you can see we get 1, 0, 0, 1, 4, negative 19, negative 1/2, and 5/2. So you see now we have this, we have the 2x2 identity matrix, and then we have that matrix of other stuff after that. This matrix of other stuff, this piece right here, that is what my identity matrix is going to be. So this means that A inverse is equal to 4, negative 19, negative 1/2, and 5/2. So there we go. That's how we do the 2x2. let's go on to the 3 by 3. And actually, very shortly, we're going to see that there's a sort of handy little formula to help us figure out what the inverse of a 2 by 2 matrix is. It's not a complicated formula. It's actually really nice. And if you know that formula, finding the inverse of a 2 by 2 matrix is just going to be so much nicer. So here, the inverse of the 3 by 3. Again, I'm going to copy down my given matrix. -2, -3, 1, -3, -3, 1, and -2, -4, 1. And then next to this guy, I'm going to put the 3 by 3 identity matrix. We're going to plug this guy into our calculator. We have to edit this now and make it a 3 by 6 matrix. So -2, -3, 1, 1, 0, 0. -3, -3, 1, 0, 1, 0. And then -2, -4, 1, 0, 0, 1. We are going to row reduce this matrix to put it in row reduced echelon form. And we get a nice whole bunch of stuff here. So we have actually some pretty nice values here. We have 1, 0, 0, 1, -1, 0, 0, 1, 0, 1, 0, -1. And then we have 0, 0, 1, 6, -2, and -3. So now, again, you can see that this is in that nice form of 3 by 3 identity matrix, and then some matrix of stuff after that. This right half here, everything to the right of that dashed vertical line, that is going to be our inverse matrix. So 1, -1, 0, 1, 0, -1, and 6, -2, -3. So that's the inverse of our 3 by 3 matrix. We saw the inverse of the 2 by 2 from the previous sample problem. And you could check these guys. You could take this matrix, multiply it by this guy, both ways, and you come up with the 3 by 3 identity. Take this matrix and multiply it by that guy, both ways, and you'd come up with the 2 by 2 identity. So as I said, we do have a nice formula for the inverse of a 2 by 2 matrix. It's a very simple, very straightforward formula. If your 2 by 2 matrix with entries A, B, C, D has an inverse, then the inverse is going to look like this. It's going to take the entries on the main diagonal and switch their places. So we see A becomes D, A turns into D, and D turns into A. And then we negate the entries, the other two entries. Those are also referred to as the entries on the opposite diagonal. Opposite diagonal, right there, B and C. So we then take the negative of the entries on the opposite diagonal. Then we're going to multiply each of these entries by 1 over A times D minus B times C. So I'll let you verify on your own, going back to this sample problem here. Take this matrix and do this calculation, 1 over AD minus BC times D minus B minus C and A. and you'll see that we do indeed come up with the same 2 by 2 matrix as we came up with here. So, how can we use these inverse matrices to help us solve a system of linear equations? Well, here's how we do so. If we look at a system of 2 or 3 linear equations in 2 or 3 variables, we can write it in the form A times X is equal to B. A is going to be the 2 by 2 or 3 by 3 matrix of the coefficients that are just on the variables. B is going to be the 2 by 1 or 3 by 1 matrix of numbers that those things equal. And then X is going to equal either XY or XYZ. It's either going to be a 2 by 1 matrix or a 3 by 1 matrix. Using inverses and matrix multiplication, we can find that we can solve for our variables, x, y, and z, by doing the following product. We multiply the inverse of A by that matrix B, that 2 by 1 or 3 by 1 matrix. So let's see how this is used in a sample problem here. We're going to solve this system using an inverse matrix. Negative 2x plus 4y plus z equals 0, 4x minus 13y plus 10z equals 24, and 3x minus 9y plus 6z is equal to a positive 15. I want to really just identify what are my A and my B here. A, as we said, is just the matrix of coefficients on the variables. So I'm only looking at this stuff here. Once I move things out of the way so that you can actually see. I'm only focused on these things here. I'm going to look at the numbers in front of these variables, and I'm going to make a 3 by 3 matrix out of those coefficients, or those numbers. So that's going to give me negative 2, 4, 1, 4, negative 13, 10, and then 3, negative 9, and 6. I also want my B. That is just this 3 by 1 matrix here of these numbers, 0, 24, and 15. Okay, well, we know that to come up with our answers for x, y, and z, I'm going to need the inverse of A. So we're going to do that same method that we just did. We're going to find what our inverse matrix is going to be here. So I need to change the entries. It's still a 3 by 6 matrix. It's going to be negative 2, 4, 1, 1, 0, 0. Now 4, negative 13, 10, 0, 1, 0, and 3, negative 9, 6, 0, 0, 1. I'm going to put this matrix in row-reduced echelon form. And again, note that I'm only concerned about the stuff that's to the right of the 3 by 3 identity matrix. Here's your 3 by 3 identity matrix happening right there. So I'm looking at everything to the right of that. So everything beginning with the 4, 2, 1, and going over to the right. So this means that my inverse matrix A is going to be 4, 2, 1, negative 11, negative 5, and negative 2. And then we see 17.66666, so on. That's 17 and 2/3, or 53 thirds. 8. And then we have 3.3333333 continuing on. That's a positive 10/3. So that right there is what my inverse matrix is going to be. So to solve for x, therefore, or because mathematicians are lazy and we can't write out the word therefore, we just put 3 dots in a triangular shape. X is going to be this inverse matrix that we just found. 4, negative 11, 53 thirds, 2, negative 5, 8, 1, negative 2, 10 thirds, times B here, 0, 24, and 15. And you could do the matrix multiplication by hand if you wanted, but I am going to enlist the use of my calculator here. I'm going to need 2 matrices, and first one has to be a 3 by 3, negative 4, positive 4, negative 11, 53 divided by 3, 2, negative 5, 8, 1, negative 2, 10 thirds. We need to edit our second matrix B. This is going to be a 3 by 1 matrix, and we have 0, 24, and 15. And now I'm just going to multiply these 2 matrices. A times B, and hit enter. And what do you know? We come up with 1, 0, and 2. And we can check x equals 1, y equals 0, z is equal to 2. We can check it in each of these 3 equations, and we would find that that is a completely valid answer. 2 times negative 1 plus 0 plus 2 is indeed equal to 0. 4 times 1, 13 times 0, 10 times 2. 4 minus 0 plus 20 does equal 24. And 3 times 1, 9 times 0, 6 times 2, 3 minus 0 plus 12 is indeed equal to 15. So while we came up with some ugly looking numbers here in our inverse matrix, here A inverse, we still came up with nice values for x, y, and z at the end. So this just goes to show you that even though you may come up with nasty values, your final answers may not actually be that nasty. So guys, that concludes our video on our sort of introduction to the inverse matrix and using them to solve systems of linear equations. We are going to be doing more with these matrices in the next video. But overall, nothing too bad, nothing really super complicated happening here. If you can use your calculator, as long as you know how to operate the calculator to enter matrices and do these basic operations that you should know how to do by now, then there's nothing really particularly nasty happening here. Just a couple formulas that you have to know. If you have any questions, as usual, reach out to me, guys. Emails, texts, voicemails, postcards, paper airplanes all the way from Michigan to Buffalo, New York. If you make one of those, I don't think you belong in this class. But until the next video, take it easy, guys.